We're very happy to welcome José Carrillo today as our speaker. José completed his PhD at the Universidad de Granada under the supervision of Juan Soler. He then went on to hold various research and faculty positions at the University of Texas at Austin and Universidad de Granada. He was formerly an ICREA research professor at the Universitat Autónoma de Barcelona and a chair in applied and numerical analysis at Imperial College of London before beginning his current position as a professor of the analysis of nonlinear partial differential equations at the University of Oxford. José's many research contributions have been recognized at an international level. He was elected a member of the European Academy of Sciences, Section Mathematics in 2018, and the Science Fellow class of 2019. He is currently the head of the division of the European Academy of Sciences, Section Mathematics. He is fellow of the Institute of Mathematics and its Applications and foreign member of the Royal Academy of Sciences of Spain since 2021. He has furthermore held many prestigious leadership roles in the scientific community. Today, we're happy to hear him speak about aggregation, diffusion, and kinetic PDEs for collective behavior applications in the sciences.
So thank you very much, Jessica, for the nice introduction. C'est un plaisir d'être ici et donner le colloque de sciences mathématiques du Québec. Je pourrais le faire en français, mais la part de mathématiques, je ne connais pas beaucoup les mots de mathématiques en français. Alors, je le ferai en anglais. Mais merci beaucoup pour l'invitation. So, aggregation, diffusion, and kinetic PDEs is what I want to discuss about today. I prepared the talk as a kind of colloquial talk, so I'm not gonna enter in too much detail in some of the research labs, but just to give you a kind of ideas of some of the questions in which I have had interest, with some of them more applied, some of them more theoretical, and why I find it still a fascinating field of research in PDEs and in applications of PDEs, numerical analysis, scientific computing, and so on. Okay, I decided not to work. Okay, yes, probably there is something to say here. Got it. Yes, good. Oops. So, okay, yeah, as usual, it doesn't work on here. Okay, anyhow, so so how I have, I will discuss first a bit of motivation about the problems I want to focus on, and the kind of toy problems first, in which somehow they trigger my attention to some of the questions here. And then I will give you two examples of each of aggregation diffusion models and kinetic models if I have time. If I'm getting too excited about one of them and then I don't have time for another, it's not that important. But you can ask me later on if one of the titles is more enticing to you. Okay, in any case, let's start with just the simple toy model of M particles interacting through potential U. So U is just the interaction potential between the particles that I'm assuming, if you want, that is symmetric and possibly has singularity at the origin. If you want to think about it as a radial potential, that's good enough. And you have M particles interacting through the potential U. So you can write somehow Newton's-like equations for them, in which you have your second time derivative. But here, what I'm just neglecting the inertia term, but I have damping. That's why at the end of the day, I end up with first order kind of first order models. So in which I have the derivative of the particle xi is given by minus the sum of forces acting on the particle. And each of the particle xj is producing a force of particle xi given by gradient of u. Okay, so here you, on the right side, you have this simulation of some number of particles randomly chosen on this cube, in which they are following some of these dynamics for a given potential, just to show you that the dynamics of that set of ODs is not as trivial, and moreover, the kind of steady states that you can have is difficult to guess really form the shape of potential. In that case, for instance, you have that kind of equilibrium state in which you have this kind of different connected components and is not radially symmetric. So if you want to write a kind of continuum model out of this, normally you would like to write a continuum model for the density of particles at time t, that you have a position x that you can normalize as a probability density or not, depending on your interest, on your needs. And you can say that this density is producing a velocity field at each location, very much in the same spirit as what you are doing here with particles, by just saying that each infinitesimal part of the density rho produces a force at location x given by gradient u of x minus y, and then you sum them up, meaning that you integrate. Okay, the minus sign is just a convention, and just to fix the convention, that convention is done in such a way that you have a radial potential. If the radial potential is an increasing function of the radius, means it's attractive. If it's decreasing function of the radius, means it's repulsive. So what you can do is to write then what you expect as a continuum model of the evolution of the density rho, that you would expect to have a continuity equation where the velocity field precisely is given by that formula. Velocity field given by this formula that I have here. This is a shortcut notation, can be written in more mathematical terms as minus gradient of u combined with the density rho. Okay, already proven that this is so, that when I have more and more particles, you can go from that to the equation. It's an interesting area of research, and you have to do the right scaling. I know discuss that. It's what is called the field limit scaling. Is one option. And there are many people still interested in that mean field scaling because it's not well known how to do it, depending on how singular your potential is at zero. Okay, I'm not going to enter into that. Okay, at the continuum level, I would like to now focus on a more general set of models in which I can have not only a known local term given by the gradient of u combo rho, but also some local terms. And let me explain you a little bit from where it comes, the local term. Maybe this, I do it on the board, if I have some chalk somewhere, which I don't see, I didn't check. I thought there would be chalk. Here is the right set. But chalk, I don't see. Okay, but I mean, yeah, there should be somewhere. Ah, it's here. Okay, sorry. I didn't, thank you. Didn't think about it. Okay, well, let's see if there is white. Great. So, what I these two terms, if you want, is say that the interaction potential you can just separate the attractive part from the repulsive part. Definitely part you can try to find on the active force with repulsive force or the potentials. I say that the repulsive force is scaled in such a way that the repulsive force is very strong near the origin. What that means by scaling means that essentially you're saying that this is like the Dirac at zero, if epsilon is so small, in some sense. With the right sign, I'm putting plus because precisely need to be like decreasing, like a very strong repulsion potential at the origin. So if you do just formally this, you will recover that term that I wrote in the previous slide, grad u combo rho, that is the velocity field, modulo sign. It will be the attractive part minus, if I do this and I substitute formally the delta, what I get here is gradient rho. So for the PDE, that term would be, okay, let me forget about the subscript here. I mean, I call it u, so you like I have it there. So you can be attractive, but could be also some part positive. It doesn't really important. It's not really important for what I'm going to say. But here, what you have is divergence of rho gradient rho. Okay, so what you get, at least formally like this, is this term that for some people in the audience know that is usually referred as the nonlinear porous medium equation of exponent 2, or nonlinear diffusion. It's a degenerate diffusion because the coefficient of diffusion is depending on rho, and it is degenerating when rho goes to 0. Okay, so general thing, I can write here function of rho, P of rho. I assuming that P is increasing to have a diffusion term there that it may be degenerate or not, but it doesn't really matter for the discussion I'm going to have. So here, the interesting question that you would like to know is for which interaction repulsive attractive potentials do you get convergence towards equilibrium or not? Those are non-trivial steady states. How you can characterize those steady states in terms of their qualitative and stability properties. And if we have this case in which we had the repulsion model by diffusion, and we have this only as attractive part, in which sense we can talk about balance between attraction and repulsion? In which sense, under which conditions on U and on P, we can talk that there is a balance between the two effects, fitting effects. Okay, so one thing that is one characteristic of that particular equation that is very important in order to discuss is to realize that there is an important gradient flow structure behind that equation. And also, if you want even first, that there is a very natural Lyapunov function for the equation. And the Lyapunov function for the equation is what is usually referred as the free energy of the system, because it is a term that comes from statistical mechanics. And it has two terms. The first term is the total potential energy. You can see U come up with rho as the potential generated by the density rho, multiplied by rho is the total potential energy. I put the 1/2 for convenience. And the second term, the blue term, is just the integral of a nonlinear function of rho that will lead to the term related to the P in the previous slide. I will show you in a second. This is something that we did a long time ago with Robert McCann and Cedric Villani. And in fact, I'm not going to explain too much about the gradient flow structure today, just to say that, in fact, you can even find then an answer to the question of balance between attraction and repulsion, even without the diffusive part under certain conditions in some of these papers. In any case, the point I want to make is that these equations, they have all this structure. By the way, I didn't have the time to fix one typo. There are typos here. That shouldn't be there, and that should be a 5 second. Okay, so yeah, I got probably an old version of it. Right, anyhow. So under certain condition between MP and rho, this one is this one, P prime is equal 5 second with this notation. So you can write the equation in that form, meaning that you are writing it as a continuity equation where the velocity field is minus the gradient of the variation of the free energy with respect to rho. And the free energy is the variation of the free energy variations conserving the mass of rho. You are conserving the mass of rho because the PDEs that are involved in principle should conserve mass. There should be evolutions of probability densities if you are normalizing. So it makes sense to impose that constraint. So if you do the variations of rho conserving the mass, you see that the variation is given by this formula. You come off with rho plus phi prime. And by choosing P and phi such a way that P prime is 5 second, then you see that it can be written in this way, the equation I have in the previous slide. Okay? By the way, in this way also you see that phi typically is a convex function of rho because P prime, because it's related to diffusion, is an increasing function. Okay, so just typical cases. If you have the heat equation, the term is the Boltzmann entropy. Entropy is the integral rho of rho. If you have a nonlinear diffusion equation, let's say with the exponent m, you will have there the LM norm constant. That's what the function phi is. Okay. So, and when it's delta, it's absolute value rho? Repeat again.
And what's the case where you get a delta when phi is something like absolute value?
When you get, you mean like a concentration?
But getting a delta.
Yeah, I mean, you mean these, that for the potential, you mean? In that case is where you will get the gradient rho is the integral rho square. You get just the L2 norm.
Square.
Yes, yes. It corresponds to just exponent m equals to 2 in the nonlinear diffusion. Okay, probably I forgot to say that is the important. I said that is a Lyapunov functional, but here you have it clearer. Formally, at least, if you compute the time derivative of the free energy along a solution, assuming that you have a good solution, it should satisfy these K. Okay, and in fact, that's crucial to even define good solutions, find solutions that do exactly this law for the decay of the function. Okay, so from where it came, my interest on this, and in fact, that's the second part of my motivation here, is these collective behavior models. There were mainly two problems years ago that attracted my attention that lies in this business. One is self-movement by chemotaxis. And this is a very famous problem in math biology, which is how to describe the self-movement by chemical cells attracted by chemical cues. Okay, so here, in fact, in that video I had there, I can reproduce again, maybe not, yes. You have just several cells and somebody with a pipette that is putting the chemical for which they are attracted to, and they direct their movement towards the source of that chemical. So Keller and Segel, that were biologists at the beginning of the 70s. By the way, it's interesting to know that Evelyn Fox Keller was the wife of Joe Keller at that time. And it's one of the authors there. So they came out with the idea of modeling this by saying that typical trajectories of particles here should go up the gradient of the chemical substance. And then, since they didn't know how to model many other things, they just added Brownian motion to it. So the original Keller-Segel model was particles will follow up the gradient of the chemical substance minus the gradient of C plus Brownian motion. So the typical equation that you would get for the density of cells, N, that I'm denoting in this slide, is an equation that resembles what I had before, a drift, which has the gradient of C. C is the chemical, the concentration of the chemical substance to which they are attracted to. And here you can have a linear diffusion as in the original model of Keller-Segel, but you could have other terms here, like volume constraints, and then you can have a nonlinear diffusion. For instance, there is this group in University of Alberta in math biology has worked a lot, Thomas Hillen, on that particular problem of nonlinear diffusion. Then for the chemoattractant, what I wrote is a simple reaction diffusion equation. And in the original model of Keller and Segel, it was assumed that in fact, it was for certain bacteria that is known that the bacteria produce the quantity to which they are attracted to. It's a way of signaling between the cells. So then that's why there is a right-hand side here that is proportional to the cell density. So they are self-attracting in some sense. And this equation, that's the original equation of that they wrote, that's the original system. You can simplify by neglecting the blue terms. If you simplify the blue terms, as you can say that the degradation is not important and that you are in quasi-stationary state, you can solve C in terms of N and substitute it there. And if you assume that you are in 2 dimensions, like in the Petri dishes experiments that they were doing in the 70s, then you solve this by the log kernel, which is the Newtonian kernel in 2D. And then you get exactly one of the equations that we had before with a log kernel and linear or nonlinear diffusion. So this is one of the classical problems that lie in this family of equations. Another one came when I did my sabbatical in UCLA. It was in 2008 that Adam will remember because he was there most of the time too. And at that time, the group of Andrea Bertozzi, Maria Rita Dorsonia, Lincoln Chase, and others, they were interested in trying to model what is called swarming. So it's they are in fact particle models to try to explain the formation of this of large scale kind of coherent structure like this meal for fish show that you see in this picture, out of assuming rules of interaction for the individuals forming the group. So some of these models are based on simple rules like an area of repulsion, an area of attraction, and an area of orientation also in terms of the velocity. They're a bit more complicated, but they are quite really in spirit. So I'll show you one of them. That's one of the most famous stats that were from side, and there was this paper of Andrea Rita Sonia, which is a kind of Newton-like equations. So you see x dot equals v dot equals, you see the last term is very similar to what I had before, just again an attraction repulsion between the particles. And the first term here is its only role is to fix the asymptotic speed of the individuals. Say that if there were no other term, you see the velocity, you do the dot product with the velocity you have for the speed for modulus of B as close ODE, and you can see that B, typically particles which are moving will tend to have a speed of the square root of f over beta asymptotically. So you're trying to have fixed speed of the individuals due to that term, and then the attraction repulsion that typically for again for a biologically reasonable potential should be something like that. An example of that would be to choose Morse potentials for the interaction, a combination of exponentially decaying functions of the radii like this to model that kind of potential. And what is the interesting thing about it? Now again, okay, they are working. So here I have a simulation again of some particles. The center of mass of the particle is at the center of the window, so the window is moving, really. And you see that while I was talking about already, something was happening here, saying that after a while, these, in this case, they decided to produce this kind of asymptotic state in which all the particles are moving translationally into some direction. The arrows are the velocities. And you see that they are organized in certain particular shape. But you can check that the shape is given by a steady state of the same problem I had at the very beginning in my first slide. So the particles are just situated at distances that such that the sum of the gradient of u of xi minus xj is equals to 0. While in that case, while I was talking, I mean, there was things going on, but now you can see what happens. Finally, they arrive to, again, some other asymptotic state. In that case, a more complicated state in which particles are rotating with a speed, fixed speed, but angular speed, the distance to 0, and they do kind of milling. Did you look at it too much? You're going to get dizzy, so I'm going to spend past the slide. Anyhow, you have a bit more complicated things. So what was interesting about this is that this is for the two of them simulations are for the same value of the parameters. Okay, so just the initial data is different. So you can have different asymptotic behaviors depending on different basin of attractions of these particular time-dependent solutions depending on your initial data. Anyhow,
but the density, the density in X is the same, but B is different. Is that
right? Right. Yes. I just chose different initial data for the velocity.
But if you just look at density, X.
Yeah, and the same number of particles, yeah. Okay, and and finally, I want to show you another example using particle system. This is much more modern than the other thing, but I think it's also links with other interesting questions that you can do with interacting particle systems that now more in fashion. Okay, so well, it cannot be more classical than trying to minimize just a function, but nevertheless, I would like to find an algorithm to do global optimization, even if the function is not too nice and smooth. And I don't have to convince you that that's an important technological question. And let's assume that we have a function that the one that we have here in 2D, which have plenty of local minima, but it has one single global minimum. So I will show you later on the algorithms that we are using, but you can use particle simulations. I mean, very much related to the collective behavior models that I showed you before to try to produce that task. I'll come back to that later. Okay? So it's just like in the movies. Okay? I'm just telling you something for later. Okay, so a preview. Good. So let me see. For the rest of my talk today, I have organized it as a 3-course meal. I have been told that food is very good in Montreal. So that I said, okay, 3-course meal then is what I have to prepare. So I have a first dish, a second dish, probably in the first dish, there are even appetizers. Then the second, the main, and then I will have the dessert. Okay, I promise. Okay, so let me explain you some other applications of this type of models. So one thing that I got very much interested in lately is in using these aggregation-diffusion models to biological problems. And the story came from segregation and mixing different cells. This was an experiment that Hideki Murakawa showed to me. I mean, Hidero Togashi is the biologist, Murakawa is a mathematician. And he was showing, and he works in the finite volume schemes for nonlinear diffusion equations. And he was talking to this guy in which he was doing this kind of experiment. I'm going to try to explain you in the easiest possible way. This experiment is using the same type of cell, which is kind of a synaptic cell from mice. And they are doing just, they put this aside and then they give them food to start reproducing, kind of, you have some kind of growth here. But essentially, you can think about this as a kind of tissue growth. They are just growing, and then they see what happens when they meet. Okay? So in the first one, even if you have this fluorescence in red and green, there is no difference between the two types of cells. This is just a way of having the two families of cells with different fluorescence to see what they do. So when they meet somehow at a sharp interval. In the second one, the only change they did is that they know there are certain genes that knock down the production of certain proteins that are related to cell adhesion between, or adhesivity properties between cells. So they can tune the cell adhesion strength. Okay, they are more attractive or less attractive, and they can tune it in different ways. They can tune it by saying, the green, they like the green more than they like the red, or they can also do it in between them. Say that they like the red like more the green, and vice versa is different. Okay, so they can tune different type of proteins in which they know the effect, because they have done experiments before, they know the effect of that. In the second one, don't ask me which one is the one that is now tuned. It should be written here. It doesn't really matter. I think it's the green. So what happens is that when they meet now, they don't meet into a sharp interface, but there is an invasion of one type of cell into the other. So the question is, from where it comes this? And the only thing that they really know is that they are controlling in some sense, or changing in some sense, cell adhesion. So we look at that from the perspective of this kind of particle systems. So we started with was a system of two types of cells, red and green, and write a kind of system now of aggregation diffusion equations. I'm going to show you that in the next slide. But let me show you first what it comes out of the kind of academic example. Here is just an initial data, which is the same for the 4 simulations, which is a bit random initial data for both densities. And as you can see here, I'm writing these numbers, Aij, Aij is just the strength of the potential between each of the two. So it's red with red, red with green, green with red. It hasn't got to be symmetric. And the shape of the potential is the same for everyone. And just changing the strength multiplied by a factor. Let's assume that the potential is just the characteristic of a ball. In fact, this is what we used. Okay? So then you just change the strengths. And here is just a schematic way, vertically, of what we're doing. All are equal. Here, this one, green likes the green more than the rest. And so the interesting thing is that by just changing those parameters, you can really show that, I mean, you can, in some particular potentials, you can show that in with the numerical scheme, you can see that this is quite robust. You can go from this kind of steady states in which you have some mixing, kind of random mixing a little bit between the two types of cells, to that kind of organization, which we call engulfment, in which one gets surrounded by the other, or this one, which is a kind of partial engulfment, or that one that finally leads to segregation between the two. So, and in fact, this is a biological hypothesis that was introduced in the 60s by biologists that is called Steinberg. This biologist just said that that's the way in which, in normal conditions, there in early embryos, there is the segregation between different cells that produce certain organs. And he already described that he would expect to have that kind, due to differential addition between the cells, you will have naturally cell sorting happening in the system. So we were quite encouraged that the model was not that bad. And in fact, then we went to the model that I will show you at the end in the next slide and try to mimic exactly the experiment of Murakawa and Togashi. They had more experiments in which they know, again, more or less some of the, how they have tuned more or less the different strengths. And here you have a simulation of our numerical scheme in which the parameters have been well adapted, in the sense that we have chosen the right the parameters that they know from biology, and the other ones that we don't know, we have chosen the best we can with some certain optimization in this kind of problem. And the results. So experiment having simulation, they will capture the main phenomena about that I don't have any mixing and sharp interface in the case of equal strands. And as soon as you have some differential addition between the two, you have some mixing. And we were able to do it even kind of predictive, in the sense of how much is the region of mixing. And you have other effects, this one and that one, in which you have this one is pushing the other density without sharp interface, so some kind of asymmetric invasion. So the scheme somehow was, I mean, the numerical method was obtaining more or less the phenomena observed in the experiment. This we did for other things, but let me just mention now, as an example of this part, what's the model that we were using. So the model that we were using is a system of aggregation-diffusion equations. You have these potentials for the two types of cells, W1, 1, 1, 2, 2, 2, 2, 1, but they were the same, set the constant, as I said, at the end. All of them attractive to each other. You can do also with attraction, repulsion, and play the game with that and for other experiments. The typical potential that we use, it was like this. Attractive in certain range of the distance between the cells. We were modeling the cells as points for the nuclei. Why to have the attraction at a certain distance? Because they know in many experiments that the interaction between the cells is not done really it's done through long protrusions. The cells produce fingering, and these fingers, when they touch, is when they produce a binding or not. So that's why it makes sense to do it non-local. And we introduce on top is a very strong repulsion, very much in that spirit. If the distance is short, we introduce volume constraint. So if the cells are very close, we just introduce a very strong repulsion that at the end, the macroscopic model, it leads to that kind of term there, but with the total population. In this case, instead of being just rho, it's rho plus eta. So you get this system in which you have self-diffusion, nonlinear, but also cross-diffusion by doing that. And that's the model that we used. Okay. So, we were quite happy with this because we were able to reproduce that kind of behavior. We use it in other math biology models, but I prefer to skip that one right now. How much time do I have left? Just to... Yes, okay. So for the more analysis-oriented persons in the room, I just wanted to mention that for this kind of question, there are plenty of interesting problems from the math analysis viewpoint. For instance, we saw the formation of these steady states, which are completely supported just in the simulation of this system of 2 by 2. But you could ask yourself, can you find the balance between attraction and repulsion even with one? Is it easy to show that you have this kind of global minimizers which have that kind of shape? So in fact, that's by itself is a very interesting question. And here I'm showing you another simulation of that case. Here, the potential is the attractive Gaussian. It cannot be smoother than that. Okay? So just a Gaussian for the attractive Gaussian versus the nonlinear diffusion. And what you can see here in the simulations, this is in 2D, that one in one dimension. I will run it again. You can see in both that they try to form local clusters, and then the clusters, they eventually merge into only one. But it can take very long time, as you pay attention to the time scales there, can take very long time for this to happen, and the reason is quite intuitive. There is only the attraction coming from this Gaussian, that if you are a very long distance, the Gaussian is really, really weak, but eventually it will kick. Okay? So,
these are particle or density simulations?
This is density simulations, everything. This is finite volume schemes. Yeah, that's the finite volume scheme that we developed with good properties. The decays the energy and all of that. So the question is, can we even prove in this case that we have what we see in the simulations, that you have a unique radially decreasing stationary state completely supported that attracts everything modulo translation? Because obviously the equation is translational invariant. So this, in fact, is a question that is still several parts of it is open. And what I can tell you is one thing. What we were able to show is that this large family of equations, sorry about the change of notation here with the interaction potential, should be U. Again, I chose probably an old, yeah, I'm going to skip this one, sorry. Yeah, in fact, that one I should have just erased it. This one, that's what I wanted to show, in fact. Here it has the right notation with a U. Great, fantastic. So we were able to show that this equation, and I'm writing it now with the nonlinear diffusion, just a power law and the degenerate case, but it's a bit more general, the result than that. But if we have a potential that is fully attractive, so no matter what the distance, at what distance you are, so that's the important thing is here. Omega prime is really positive. That's the derivative of the potential as a function of the radius. Some other technical conditions, it doesn't really matter. We can show that under these conditions, that include, for instance, the Newtonian potential in a dimension, then all stationary states of this equation are completely supported, radially decreasing, And in some cases, we can prove that they are unique modulo translations. Okay? And this was not an easy thing because you had to talk about the first steady states and so on. I'm not going to explain that much, but it's part of this paper that we wrote in. So there are plenty of interesting open math analysis questions here that we don't know. For instance, stability of those, we know very little for the time evolution problem. We know only the cases of Newtonian potentials, essentially, for the convergence in time. And the difficulty is already somehow, here. Even in the title, I wrote it, metastability, because the difficulty is that you can have, like in this case, that the convergence really can be very, very slow. Okay? So just to give an idea of convergence and when you have better decay rates, depending on how increasing the potential is at infinity, these kind of things, it would be very interesting. Okay, just to give a more analysis kind of question. Let me see if I can. Yeah, I'm trying to pass some slides without having you a little bit dizzy here, but it seems it's more difficult for me to do it today. So, yeah, okay. Yeah, okay. Let me go. Sorry. Yeah. And I think I will, I was preparing to give you more, another sample of the interesting behaviors in these models, which is about phase transitions, but I'm not going to discuss that. I'm going to skip that part of my menu. I'm sorry. The chef decided that we are late. We had to close. The table has to be given at 9. Okay, so, and then we go to the dessert. Okay. So, but let me tell you that one thing about phase transition is another aspect of long-time asymptotics that is very interesting in these models, that you can have potentials and nonlinear diffusions, or even for the systems in which you have much more than one stationary state, how many stationary states you have, how stable they are. That is really a big, big open problem. We have characterized some samples in which we can say how many steady states you have. But even if you have how many steady states, it doesn't tell you the long-time asymptotics at all. You will have to classify the basin of attraction. And even if the problem looks simple, these models, it's easy to see that they have, it's easy to give examples that they have this phase transition. Okay? So let me give you the dessert of this kind of type of modeling, the application to global optimization. Yeah. Okay, so again, coming back to what I said before, there are plenty of things that people have tried for global optimization. Most of those things that people have tried, as you know, they are, from a mathematical point of view, they are not proofs, they are meta-heuristics. We don't know convergence proofs of many of the methods that people are using for global optimization. We simply don't know. But they're, I mean, they work sometimes, they are better or worse. They have all these comparisons of global optimization with success rate and so on. But can we do something similar to this idea of consensus that I show you, that it appears in these models of swarming? Remember that some of the simulations, in one of the simulations that I show you, the particles at the end, they agreed in some sense to move in the same direction. Okay, so there was a consensus in the velocity. So I want to follow some idea, some similar idea to that at the level of the problem of minimizing a function. My connection to that at the beginning was just by reading some papers on the particle swarm optimization methods, which were somehow quite connected to that models from Andrea and company. In fact, they don't do what I'm showing you here, but they do the best particle, I mean, at the discrete level. Anyhow, what we do is the following. So let's assume that we have n agents. My agents are moving in the landscape of the function f. Okay. The objective is to find the location of the global minimizer of f. And the only thing that they can do is to exchange the information. So I not that evaluate the function as it's easy. You make your life complicated to your competitors. Computing the gradient is difficult. Okay, or bad, or less accurate, or impossible, whatever, depending on the dimension where you are. But I can evaluate easily the function. So what I do is the following. Each particle is gonna get in the direction of certain consensus point. And the consensus point is gonna be a kind of average of certain quantity that I call omega f. Omega f is gonna depend on the function f. I will tell you next how I choose omega f. So this is a kind of average of that. And then I add some noise, and the noise is degenerate. Why I do the degenerate noise? Because I want, when the particles are agreeing in some direction, that the noise has lesser effect. So I want typically to have some concentration eventually. Okay? Now it comes how I choose omega f. Okay, so I choose omega f as e to the minus beta f. There are two reasons why we did this. First of all, because if you think in terms of the easiest simulated annealing method, which is one of the methods that was there for many, many years, it's just the linear Fokker-Plan equation, where you use f as the potential of the linear Fokker-Plan equation. Then the stationary state of that linear Fokker-Plan equation is precisely e to the minus beta f normalized. There is another reason, e to the minus beta f, when beta is large, beta is like the inverse temperature of the linear Fokker-Plan equation. When beta is large, you expect to be concentrated at the location of the global minimum of the function f. It's going to be peak around the global minimum as beta is getting larger and larger. In fact, there are two things here. The motivation of choosing that is because when I send n to infinity, that average I do is like doing the average of the probability measure e to the minus beta f rho. Okay. So it's kind of Gibbs type of measure associated to the density of the explorers, say. And also, if we want to be more quantitative, there is Laplace principle that tells me that if I have a probability density, forget about the t here, have a probability density rho, and I send beta going to infinity in this expression now, the log of the integral e to the minus beta f rho, when beta goes to infinity, then this is the infimum of the function f. Okay? So the idea being that what I would like to have is, I would dream to have that this measure, when t goes to, say, infinity, it will approach a Dirac at the location of the minimum. Okay? So we call this consensus-based optimization. And this was introduced first in a paper of a postdoc of mine, Stefan Martin, that I discussed with him some of the ideas. He did first a paper on numerics of it with René Pinau, Claudia Totzek, and Oliver C. And then in another paper with Jean-Pil Choi, Oliver C., and Claudia Totzek, I, with them, studied the theoretical side of it. So these are the simulations I already showed you. So you have some number of agents here, very small number of agents in 2 dimensions, but you already see the idea. here 30, here 10, in which you had just the evolution of those, and eventually they arrive to the location of the minimum of the function. What we were able to do is the following. We were able to prove, really, passing n to infinity. We did the mean field limit of the m particle system. Then the mean field limit of the m particle system is that nonlinear Fokker-Planck equation, which is not a gradient flow like before. It's not in the same speed as before, but very close. Has very much the same type of structure. You have a drift, but now it's time dependent with that average. You have a diffusive part, but now again, non-linearly depending on averages of the density. Okay? And here you have just a simple simulation of the PDE in one dimension with one of the complicated functions I had before, just to check that eventually what we said that the initial data gets concentrated around the location with respect to the location of the global minimum. What we were able to prove is that under certain assumptions on the ingredients here, sigma, lambda, beta, and for general functions F, but just C2 functions, then if I choose the initial data in which implies that I'm already a bit close to the global minimum, if I choose the initial data well, first we have consensus, meaning that as t goes to infinity, you converge always to a Dirac at a point. And if you choose the beta large, the point can be as close as you want to the location of the infimum. So if you allow me to use infinitely many agents, if I can use infinitely many butterflies and drop them in Yosemite Valley, I can find the minimum of the valley. Okay, this is what I'm saying. Can I do that with a finite number? So that would be good to have a result like that. And then I don't know how to prove it with a finite number and to give explicit estimates. There are several people working in this direction at the moment. Consensus-based optimization and sampling has got a bit of in which plenty of people were interested in. So, but still, we don't have that kind of result. Okay. In any case, I think it's time to finish. So let me just explain you that. So let me just tell you that I hope to have convinced you that using agent-based model or this kind of particle models are a powerful technique to connect between microscopic and macroscopic scales that can be used in different applications. They both, although I didn't talk too much today about kinetic models, that was the phase transition part, I skip. They are both first order or second order lead to aggregation, diffusion, or kinetic models, the second order models. And their approximations, they are very natural continuum descriptions for that type of modeling. There are beautiful theoretical questions around these PDEs in terms of calculus of variations and stability analysis. And qualitative questions for these systems, like phase transitions, steady states, stability. They are well, I mean, we are starting to understand them, but still plenty of interesting open problems. And these are just a list of some of the papers I used for my presentation today. And thank you very much for your attention.
Thank you very much, Jose, for a wonderful talk. Do we have any questions? Yes?
Sorry, what was the case of phase transition driven by noise? What example? Can you yeah.
Yeah, I skip. That's yeah, no problem. You are Sergey, no? Yes, no problem. I skipped today the example, but I can tell you. Let me see if I can go back there without getting people to. Let me see. What's the easiest way to show that? Yeah, probably this one. I mean, it's a kind of it's this equation that you have in the first line of this slide is an equation that is a distribution of probability in velocity space, in which the first term is relaxation towards the mean velocity. The second term is very similar to the one of Bertozzi and company, which you have the gradient of a fourth order potential. So you have a kind of double well potential velocity, which leads to this. And then you have linear diffusion. So what you can show on this one is that, in fact, let me just say that what you can show in terms of the steady states is that there is a critical value of the noise, D, such that if the noise is large, you have only one solution. But if the noise is small, you have at least three, well, in fact, in some cases, we know you have three solutions. Here I'm showing you the one that is non-trivial, the one that is not zero, which is the attractive for the dynamics. So you always have the one corresponding to U equals zero. So let me just say three solutions below, three stationary solutions below a critical value that depends on the noise. And only the homogeneous, only the Maxwellian solution for the larger value of the noise. And you can identify even the critical value of the diffusion. So you have plenty of situations also with nonlinear diffusions in which you have this kind of behavior. So that's what I referred about phase transition driven by noise.
Thank you.
No problem.
Other question.
For the optimization, the last part, do you have, I didn't maybe I did not get, do you have error rates or rates of convergence for the in terms of n? I mean,
No, that would be the dream. If I had that, probably I will be working for Google
exactly.
now.
Okay. And is there any hope? Probably not, but I mean, you're already taking a mean field limit that you have the Fokker-Planck equation of applying that to an infinite dimensional energy landscape.
I never thought about doing in infinite dimensions, that kind of thing.
Okay.
Never thought about it.
Okay. Because I mean, that's what in calculus is so hard, all these energy landscapes, which we...
Yeah, I mean, of course, in practice it's because you are in very large dimension, but it's finite.
Yeah.
Okay. So, I mean, of course, you're not going to use the PDE. That's just a theoretical understanding of what is going on.
Right.
It's just that you would like to know how many particles you would like to put in such a way. If I give you a function with certain properties, in order that you have a good approximation of the minimum. But that's what we don't know.
Any other questions?
Yeah, I was curious about the assumptions on F in this last part. You mentioned on passing like F has to be C2 in your theory.
What I need is bounds on the gradients and the Laplacian, and essentially, you know, I just need that in the outlet because what we do is that assume that it has quadratic growth outside outside of the gross quadratic things. What the assumptions I'm doing is just that I have bounds.
C2 would work.
I never tried to do a piecewise C2 of that. I would. I mean, there is no any problem using there is no any problem using the scheme, and I would say that most likely it's going to give you nice results. But the proof that we give, it makes use of those bounds. This is what I mean. The proof that we do for the PDE, you see. I mean, not. But that's what I'm saying.
You do get a problem in global optimization if you have even like an unbalanced asymmetrical. It probably needs. Otherwise, they keep shrinking.
There are other things that we have done in the direction of global optimization, but I mean, if you are interested in on that, we can discuss it aside. We have, for instance, changed the type of noise to make it, instead of doing it as isotropic, to make it component-wise. The reason being is that our estimates on the convergence, they depend badly on dimension. So one question of the reviewer at some point was, but it's really practical because it depends on dimension. So we can get rid of the dependent on the dimension in the conditions of convergence. And we had used it with a collaborator in some machine learning business for MNIST data set. I think we use it for the MNIST data set. The dimension of the space we were working is around 8,000. And with some additional changes in such a way that you can make it really work efficiently. Yeah.
This is also very good. Could you just give me a feel for the intuition of the scaling for the terms? Did you choose it because they're the best, or do they matter?
You mean in the equation, the lambda, yeah, I mean, okay, do I have, the important thing is that there is a relation between lambda and sigma in such a way that we can control the variance of the distribution, that it goes to zero as t goes to infinity. And that was the one that was depending on the dimension, that we got rid of it with a different noise. So there is a relation on lambda and sigma that it has to satisfy. And then you have the choice of the beta. What is important on the beta is that you have to take it large enough, because if not, yeah, I mean, this, you have to, the beta has to be large enough in order to control that is closer and closer to the location of the minimum. So, and we have in the proof, we give some condition again on the beta. That's in practice, you can do it with much less.
And does it matter if it's x minus nu absolute power 1 or power 2? I mean,
you mean in terms of yeah, also which yeah, you're referring to, let me see, you're referring to this, sorry, let me go back here. Yeah, so if it depends on the modulus here or something different. I mean, we put the modulus there just to have some noise for which we can do something theoretical, but there is no any particular reason why, to tell you the truth.
Okay, that's what's
and yeah, not me, but other people look at the variant that, as I said, we did this component-wise noise instead of isotropic to avoid this bad dimension dependence on that term. But still, the choice of noise, you see here at this point, you don't care about anything. You just choose the one that brings you, you know, that it does the job, exploring enough. Mm-hmm. That you don't get trapped in local minima, but that you can somehow compute easily.
So just a comment, what I like about this, we had a speaker in global optimization, Katja Schoenberg, recently. And, you know, they have textbooks on this stuff. But one thing they said, they studied the case of sort of wider stencils, like densities. And all the stuff, all their theory is based on local stuff. And they said they know that going broader is good sometimes, but they didn't have theoretical techniques to analyze it. Mm-hmm. This is all a Taylor series. Mm-hmm. So I think they might be interested in these results. If there's a way to meld, you know, to merge this with their.
I mean, this is just a completely different viewpoint.
It's a completely different view, yeah.
Exactly. That compared to even a stochastic gradient descent or things like that. Exactly. Non-local. That is fully non-local. Yes.
Which is cool.
Yeah.
Sorry, and how omega F is connected with F on this picture?
Yeah, this I had it in the, yeah, that was the e to the minus beta F that I had here. Yeah.
Thank you. Yeah, thank you.
Yeah.
Do we have any further questions? Further questions on Zoom? No?
I might be wrong, but I saw you had a slide. Sorry, a slide with a fish. What was that example about?
The slide with the
with a fish.
Yes. With the fish. You mean at the very beginning? That was only to show this kind of models for swapping. Yes, of the different orientations and regions of the interaction between the particles. No, nothing more than that.
Okay, if we have no further questions, let's thank Jose one more time. There'll now be a cocktail reception and the 6th floor lounge.